Hey folks, let's work through worksheet number 1, thermochemistry. This stuff should be pretty simplistic. Use kinetic energy to explain the difference between evaporation and boiling of a liquid. All right, well, when you think of molecules, when we talk about energy, we have a bunch of molecules here. All right, and they are all moving. And this is the speed at which they're moving, which is represented by this graph. Okay, think of this as kinetic energy, if you will, how much kinetic energy the molecules have. And the average kinetic energy gives you the temperature of the molecules. But what that tells you is some of the molecules are moving faster than this and some are moving slower. And if you get some that are moving way fast enough, which are way over here, all right, they, for whatever reason, have a huge amount of energy, right, they can actually leave the surface of the liquid. So if you think of this as, here are a bunch of molecules all bouncing around, whatever, because they're all moving, okay, and all of a sudden a couple of molecules, 3 or 4 or 5 or whatever, all hit one particular molecule. And so they all transfer some of their energy to that one particular molecule. That molecule has so much energy it leaves the surface of the water, right? That is called evaporation. Okay, now what happens when we get a lot of molecules when the average is way over here? All right, where there are lots of molecules over here that have more than enough energy to leave the liquid. Well, this is called boiling. Right? These are all leaving the liquid, and when they leave, they have to take a little bit of these guys' energy, so they go back here a little bit, and then they work their way back up, and because they're given more heat, they're sitting on a stove or whatever until they get over here, and then they can boil off. Right? So it all depends on how fast the molecules are moving, and hence that's the kinetic molecular theory where we're talking about molecules. Sorry, wrong way. All right, is a forest fire endothermic or exothermic? Remember that endothermic means it is absorbing heat from the environment, and exothermic means it's giving heat to the environment. And a forest fire is definitely giving heat to the environment, so it is exothermic. And egg frying, you have to kind of think of the whole system here. The egg is getting hotter. The egg is absorbing heat from the stove, so the egg is endothermic. Now, the stove is exothermic. The stove is giving up energy, right? Where is it giving it to? It's giving it to the frying pan. The frying pan is hence giving it to the egg. The egg is frying, so the egg frying itself is endothermic, right? So you need to kind of think about exactly what the question's asking, right? Here's another perfect example. The propane burning in your gas grill. Well, the propane is giving you energy. It is releasing energy to the environment. It's releasing energy to the area of the gas grill. The gas grill is getting hotter. That is called exothermic. However, the hamburger is cooking on the gas grill. So the hamburger itself is absorbing energy from the gas, from the propane, to go and get hotter. And so the hamburger, sorry, that's wrong. I circled the wrong one. The hamburger is endothermic. It is absorbing energy. Okay. So hopefully that helps a little bit. As you increase temperature, what happens to the vapor pressure of the liquid? As you increase the temperature, the vapor pressure gets higher. We saw that in one of our tables where the vapor pressure rises as it gets hotter. In other words, more of the molecules have enough energy to leave the surface of the liquid. So that vapor pressure is going to increase. Think of it as you've got a bottle. All right, I'm not even going to draw it. Okay, here you've got let's say that's a bottle, okay? And you got another one over here, all right, that's got exactly the same amount of stuff in it, okay? And this one is at 20 degrees Celsius, and this one is at 40 degrees Celsius, all right? Well, what happens is this one, and by the way, they both have liquid in them, all right? They both have liquid. This liquid is going to tend to want to evaporate more than this liquid is. So let's put 2 arrows over here. We only put 1 arrow over here. So more of this liquid is evaporating, and because more of this liquid is evaporating, there is a higher pressure up in this area, because this area is all the gas pressure up here. So there are more molecules hitting the inside, so your vapor pressure is in fact higher. All right. Can you boil water at room temperature? We showed you this with the bell jar. We definitely can. And why is that? Because boiling is defined as when the vapor pressure equals the atmospheric pressure. Okay, so if you remember, we put water inside a bell jar, and here's water sitting in there. It has water in it, right? And it would boil if the vapor pressure of the liquid is the same as the vapor pressure of the atmosphere. So typically we have 760 millimeters of mercury at sea level pushing down, and we don't have 760 pushing up. But when we reach 100 degrees Celsius, our vapor pressure is 760 pushing up. Okay, so let's say that our vapor pressure pushing up is only 100. Now let's not use 100 just because that can be confusing. Let's say 200 millimeters of mercury. All right. Now that means if we can lower our vapor pressure to 200 millimeters of mercury, then this water is going to boil. And that's what we do inside this bell jar. It's a vacuum chamber. We take the air out, lower the vapor pressure 200 millimeters of mercury. The water is going to boil. The temperature of the water did not change. All right. That's it. See you in class. If you have questions, let me know or let us know. We'll help you out. Okay.